There is an organ in your chest, built from nothing but air and time. Before you took your first breath, it was already forming, folding itself into an architecture so intricate that scientists are still mapping its details today. It would spend its entire existence doing something no other organ does, reaching outward, pulling the external world inside the body, and sending it back transformed. Quiet, effortless, invisible. And yet, for most of human history, no one truly understood what it was doing or why. The lungs are not pumps. That is the first misunderstanding. They do not push or pull air through any mechanical force of their own. They have no muscle tissue capable of that kind of work. What they do is something far more elegant, far more dependent on invisible physical laws, and far more surprising than simple pumping. The lungs are passive responders, architected to follow pressure, to open when the body tells them to open, and to collapse when it tells them to close. Everything happens because of forces acting around them, not inside them. But that is getting ahead of the story. Before the mechanism, there is the structure. And the structure of the lungs is, by any measure, one of the most intricate architectural feats in the entire human body. Each lung is divided into sections called lobes. The right lung has 3 of them, the upper, middle, and lower lobes, while the left lung, slightly smaller to accommodate the heart that sits beside it, has only 2. This asymmetry is not random. The human body has arranged itself with extraordinary care around the demands of circulation, fitting organs together like a 3-dimensional puzzle that took hundreds of millions of years to solve. The left lung sacrifices about 10% of its volume, so the heart can occupy the space it needs to do its own relentless work. From the outside, the lungs appear soft, spongy, and pale pink in healthy tissue. Though in people who have spent years breathing polluted urban air, the surface becomes mottled and dark, permanently stained by the particles they have filtered. This visible record of environmental exposure sits on the outer surface of an organ that processes, on average, about 2,900 gallons of air every single day. Air enters through the nose and mouth, passes through the trachea, a rigid, cartilage-ringed tube roughly 4 to 5 inches long, and reaches a fork. That fork, called the carina, is where the trachea divides into 2 primary bronchi, one heading to each lung. The body is sensitive here in a specific and useful way. The carina is one of the most touch-sensitive regions in the entire respiratory system. A single particle, a sip of fluid going the wrong way, a foreign object, any of these contacts the carina and triggers an immediate, powerful cough reflex. The body does not wait to see what happens. It responds instantly, violently, before the airway can be compromised. From those 2 primary bronchi, the branching begins in earnest. The bronchi divide into secondary bronchi, which serve individual lobes. Secondary bronchi divide into tertiary bronchi, which supply segments within those lobes. Each division is smaller in diameter but greater in number, so the total cross-sectional area of the airway actually increases as you go deeper. The bronchi then become bronchioles, smaller passages now without the cartilage rings that kept the larger airways open. The bronchioles branch further, again and again, through approximately 23 generations of division in total, until they reach the terminal bronchioles and then, finally, the respiratory bronchioles that lead to the end of the road, the alveoli. The alveoli are where everything that matters actually happens. And understanding them requires abandoning the mental image of lungs as 2 large air sacs. They are nothing like that. Each human lung contains somewhere between 300 and 500 million alveoli. Tiny, grape-like sacs, each one only about 0.2 millimeters across. Laid out flat, the total surface area of all alveoli in both lungs combined would cover an area of roughly 750 to 860 square feet. That is larger than the floor plan of many apartments. It is an enormous surface area, folded with astonishing efficiency into a space that fits inside the human chest. This surface area is the answer to a fundamental biological problem. The body needs to exchange gases, oxygen in, carbon dioxide out. And the speed and efficiency of that exchange depends entirely on how much surface is available for diffusion. By folding hundreds of square feet of membrane into a volume measured in liters, the human lung solves this problem in a way that no engineer working purely from scratch could easily improve upon. The walls of the alveoli are extraordinarily thin. We are talking about a membrane perhaps 0.2 micrometers thick at its thinnest, about 50 times thinner than a single human hair. Pressed against the outer surface of each alveolus is a dense network of capillaries, the tiniest blood vessels in the body. The distance between the air inside an alveolus and the blood flowing through the capillary touching its wall is so small it is measured in fractions of a micrometer. Gases need only diffuse across this minimal barrier, and they do so passively, following concentration gradients. Oxygen moving from the higher concentration in the inhaled air into the blood where oxygen is depleted, and carbon dioxide moving in the opposite direction, from the blood where it has accumulated as metabolic waste into the alveolar air where its concentration is lower. This diffusion is not slow. In a single pass through the alveolar capillaries, a journey that takes less than 1 second, red blood cells are almost fully saturated with oxygen. The architecture of the alveoli is so optimized for this purpose that the blood does not need to linger. It passes through quickly and leaves loaded, but the alveoli face a problem that is not immediately obvious. A fundamental principle of physics called surface tension applies to any liquid surface, and the interior of each alveolus is coated in a thin film of fluid. Surface tension in a sphere tends to cause it to collapse, and the smaller the sphere, the greater the collapsing force per unit area. Left unaddressed, the hundreds of millions of alveoli in your lungs would all collapse inward, and the organ would become a dense, airless mass, incapable of any exchange. The body solved this problem with a substance called surfactant, produced by specialized cells in the alveolar walls, called type 2 pneumocytes. Surfactant is a mixture of fats and proteins that coats the inner surface of each alveolus and dramatically reduces its surface tension. Without surfactant, breathing as we know it is impossible. This is not theoretical. Premature infants born before approximately 34 weeks of gestation have not yet developed sufficient surfactant production, and the result is a condition called respiratory distress syndrome. The lungs are stiff and difficult to inflate, and breathing becomes exhausting, labored work. The discovery and development of synthetic surfactant replacement therapy, which began in the 1980s, transformed outcomes for premature newborns and remains one of the more underappreciated medical breakthroughs of modern times. The mechanics of breathing itself deserve attention because they are fundamentally counterintuitive. When you inhale, the diaphragm, a dome-shaped muscle below the lungs, contracts and flattens. Simultaneously, the muscles between the ribs, called the intercostal muscles, contract and lift the rib cage outward and upward. These movements expand the volume of the thoracic cavity, the sealed space in which the lungs sit. Because the pressure inside a sealed space decreases when its volume increases, the pressure inside the chest drops below atmospheric pressure. Air flows in not because anything is pulling it, but because pressure outside is now higher than pressure inside. It follows the gradient. The lungs expand to fill the space. Exhalation, under normal restful conditions, requires no muscular effort at all. When the diaphragm and intercostal muscles relax, the elastic recoil of the lung tissue, which has been stretched during inhalation, pulls the lungs back to their smaller resting state. Volume decreases, pressure rises above atmospheric pressure, and air flows out. You exhale passively, carried by the physics of stretched tissue returning to its natural shape. This elasticity is maintained by the connective tissue within the lungs, particularly a protein called elastin. Elastin gives lung tissue its ability to stretch and recoil repeatedly without losing its properties over the entire lifetime of a person. It is the same protein responsible for the elasticity of skin and arteries. In conditions like emphysema, most commonly caused by long-term cigarette smoking, the walls of the alveoli are progressively destroyed, and with them, much of the elastin scaffold. The lungs become hyperinflated, trapping stale air because there is no longer enough recoil force to push it out. The surface area available for gas exchange shrinks dramatically. Breathing becomes work, hard, constant, exhausting work, for what was once the body's most effortless function. The lungs are also far more than a gas exchange organ. They serve several functions that have nothing to do with breathing in the conventional sense. The pulmonary circulation, the loop of blood flow that passes through the lungs, receives the entire output of the right side of the heart with every single heartbeat. This means the lungs are in a unique position to filter the blood. They trap small clots, air bubbles, and other particles before they can enter the systemic circulation and cause damage to the brain or other vital organs. Specialized immune cells called alveolar macrophages patrol the alveolar surfaces constantly, engulfing and destroying inhaled pathogens, dust particles, and debris. The lungs also play a role in regulating blood pH by controlling how much carbon dioxide is retained or expelled, a function so critical that the brain monitors carbon dioxide levels in the blood continuously and uses them as the primary signal to drive the respiratory rate. There is another layer to the lungs that medicine has been investigating more carefully in recent decades: their role in the immune and inflammatory landscape of the body. The lungs are a mucosal surface, an interface between the body and the external environment, and they are in constant negotiation with what passes through them. The airway is lined with a carpet of tiny, hair-like projections called cilia, which beat in coordinated waves to move a thin layer of mucus continuously upward and out of the lungs. This mucociliary escalator, as it is sometimes called, traps particles, microbes, and pollutants in the mucus and carries them toward the throat, where they are swallowed and neutralized by stomach acid. It is an elegant sanitation system running silently and continuously, and it is remarkably effective. Most of what enters the lungs never reaches the alveoli at all. Beneath the ciliated surface, the immune architecture of the lungs includes clusters of lymphoid tissue, dendritic cells that sample incoming air for antigens, and a carefully calibrated inflammatory response that can escalate rapidly when a genuine threat is detected. The balance of this response is extraordinarily delicate. An underreaction allows pathogens to establish themselves. An overreaction, the immune system flooding the alveoli with fluid and inflammatory cells, can compromise gas exchange more severely than the infection itself. The acute respiratory distress syndrome seen in severe pulmonary infections represents exactly this failure mode. The immune response, attempting to protect the tissue, ends up overwhelming the lung's ability to function. Scientists continue to investigate the full extent of the lung's immunological role. Evidence suggests that the lungs may even contribute to platelet production, the blood cells responsible for clotting, a function previously attributed primarily to the bone marrow. Research in recent years has identified what appear to be megakaryocytes, the precursor cells that produce platelets residing in the lung vasculature. Whether this represents a significant contribution to the body's overall platelet supply is still being studied. It is a reminder that our understanding of the lungs, despite centuries of anatomical work, is still evolving. The lungs also have a relationship with the brain that operates below consciousness. Breathing is unique among vital functions in that it can be both automatic and voluntarily controlled. The heart cannot be commanded to beat faster or slower by conscious thought alone. The digestive system runs on its own schedule regardless of intention, but breathing, though it never stops on its own, can be consciously altered, held, deepened, or quickened within certain limits. This dual control is rooted in anatomy. The brain stem contains respiratory control centers that regulate the automatic rhythm of breathing, but these centers receive inputs from the cerebral cortex, allowing voluntary override. The limits of that override are biological, not psychological. The moment carbon dioxide rises too high in the blood, the involuntary drive overwhelms any conscious resistance, and the body breathes whether the person wants it to or not. What emerges from all of this? The branching architecture, the alveolar surface, the surfactant chemistry, the elastic mechanics, the immune surveillance, the dual neural control, is a portrait of extraordinary design. Not the design of any engineer, but the design of selection pressure operating over hundreds of millions of years, finding solutions to problems that physics and chemistry imposed, layering refinement upon refinement until the result is an organ that exchanges gases with near-perfect efficiency, defends itself against a constant barrage of environmental threats, modulates the chemistry of the blood, contributes to immune surveillance, and does all of this while never resting, never taking a break, from the first breath at birth to the last exhalation of a long life. Every breath you take is not a simple act. It is the activation of an ancient, layered, deeply sophisticated biological architecture. One that spent the better part of evolutionary history being refined into something that requires no thought, no effort, no conscious attention, and yet sustains everything. The lungs breathe not because you ask them to, but because the body has built a system so reliable that it runs on physics, chemistry, and cellular intelligence alone. And somewhere in that seamless, invisible operation lies one of the most profound expressions of biological design the natural world has ever produced. Breathing feels simple because it was designed to be invisible. But what you've seen is anything but simple. Every breath is the result of pressure gradients, microscopic membranes, elastic tissue, immune surveillance, and neural control systems working in perfect coordination, without asking for your attention, without ever stopping. The lungs don't just sustain life, they reveal how deeply the body depends on physics, structure, and silent precision. If this changed the way you understand your own body, take a moment to support the channel. Like the video, subscribe, and stay with us here on Anatomy Unlocked, where we break down the human body beyond intuition and into what's actually happening beneath the surface.